Okay, I need to talk to you about double and triple bonds in Lewis dot structures. I want to use as an example carbon dioxide. I'd like to draw the Lewis dot structure for carbon dioxide. I know that carbon is central, and then the two oxygen will be the ligands. Carbon has 4 valence electrons, plus each one of oxygen 6 is 12, and for a total of 16 electrons, or 8 pair. I'm going to use 2 of my bonding pair to hold the whole thing together. That means I have 6 bonding pair left over to dot. All right. There's 3, 4, 5, and 6. You will notice that my ligands have an octet, but my central atom does not. What I can do is take my ligand unbonding pair and make it a bonding pair with the carbon dioxide. If I do these for both, I will have an octet for my carbon and an octet for the oxygens. Therefore, the Lewis dot structure for carbon dioxide is this. Now, as another example, here is nitrogen. To draw it, nitrogen would look like this. Each nitrogen has 5 valence electrons. That's 10 electrons total, or 5 pair. 1 pair goes to connecting the two together. There is 1, 2, 3, 4, and 5. Well, that's not going to work. So what I'm going to do is promote from the ligand some electrons, and now I have a valence electron, or a octet for each one of my atoms. Okay, now let's move along to resonance structures, formal charge, and VSEPR models. Yes, that is my cat's foot. Okay. Resonance structures occur when there are more than one valid Lewis dot structure for a particular model. Okay, what ends up happening is you write all 3 of the Lewis dot structures, and in real life, they're an average of the 3. Here we have the nitrate ion, NO3 minus 1, and you will notice that there could be a double bond anywhere attaching any of the nitrogens to the oxygens. Each one of these is valid, and they're resonance structures. If someone asked you to write the resonance structures for NO3, you have to write all 3 of them for it to be valid. Okay, benzene does the same thing. Now, obviously, if you have odd numbers of electrons, like nitrogen monoxide, it can't be handled by the LE model. It doesn't work. You can't draw a valid Lewis dot structure. Okay, I'm going to skip over formal charge. It's not heavily tested on the AP. Okay, Peanut, get your head out of camera range. Okay, that was Peanut. We're going to leave her there. It's been a heck of a day. We're going to leave formal charge out because it's not tested on the AP exam. You'll find that you will have to talk about formal charge in college. All right, now we need to talk about VSEPR and VSEPR shapes. VSEPR stands for valence shell electron pair repulsion theory. What it is telling you is the way that electrons will align themselves so as to minimize the repulsion between electrons and bonding atoms. They want to be as far away as possible. So the method to determining the shape using a VSEPR model is to draw the Lewis dot structure, count the number of shared electrons, bonding pairs, also called sigma bonds. Let's take a moment out and talk about sigma bonds. Sigma, the Greek sigma, is a single line in our thought. Okay, so a single bond has one sigma bond. A double bond will have one sigma and one pi bond. Every bond has a sigma. A triple bond will have its one sigma and two pi bonds. Okay. Okay, so you've counted your number of sigma bonds only. Now you count your number of lone pairs, and then you're going to look up for the shape, which, by the way, you will not have this chart on the AP exam. Sorry. All right. So then it's just a you counting electron domains. Alrighty. So you're going to use the chart and figure out the shape. So let's take our CO2 as an example. CO2, and we're only concerned about the central atom, always just the central atom. The central atom has around it two double bonds. Each one of the double bonds is one sigma and one pi. All they care about is the sigma. So around the central atom, there are two sigma bonds and no lone pairs. Remember, this is what a lone pair looks like. Therefore, according to your chart, the number of electron pairs around the central atom is 2. The bonding pairs, or sigma bonds, is 2. The number of non-bonding or lone pair is 0. Therefore, the electron geometry, this would be VSEPR, is linear. And the molecular geometry, which is a different thing. This is based on VSEPR, but it really has to do with a three-dimensional molecule in space. It will also be linear, and the bond angle, which you need to memorize, will be 180 degrees. Now let's take carbon tetrachloride. This would be the Lewis dot structure for carbon tetrachloride. Around the central atom, there are 1, 2, 3, 4 sigma bonds. So we look in no lone pairs. We look to our chart. There are 4 electron pairs around the central atom. We have 4 bonding pairs, no lone pairs. So therefore it would be by VSEPR, tetrahedral, by molecular geometry, tetrahedral, and the bond angles between the atoms would be 109.5. Okay, Peanut. Time out for Peanut. Really, you need to leave the area. Peanut has now left the area. Huh, such a day. Okay, now let's take NH3. NH3 looks like this. There are 4 electron pairs, 1, 2, 3, 4, around the central atom. 3 of them are bonding pairs, and 1 is a lone pair. So we come to our chart again, and this time we see we have 4 electron pairs around the central atom. 3 of them are bonding pairs. 1 is a lone pair. The VSEPR shape is still tetrahedral. However, the molecular geometry is trigonal pyramidal, and it has a bond angle that's less than 109.5. I am not going to do any more examples on this format, but I will do a pen cast of some of them. Okay, now let's talk about the polarity of a bond, and then a polarity of a molecule, and you must get these straight in your mind. The polarity of a bond is the polarity of the bond is between the 2 atoms. Just the 2 atoms. The polarity of the molecule would be how it's relating in space. So the polarity of the bond is always associated with the change in electronegativity. And you recall that if it's less than 0.5, it's nonpolar covalent. If it's 0.5 through 1.6, it's polar covalent. And if it's greater than 1.6, it's ionic. Okay. Now, a molecule, the whole shooting match, is polar only if both of these conditions are satisfied. Both must be true. The bonds within it must be polar. That's back to this. You must have a delta En that is greater than 0.5. And there is an asymmetry in the molecule. You can set your minds at ease and not worry about asymmetry and just check for lone pairs. Okay. So, if it is a polar bond within the molecule and it contains a lone pair, then it can be polar. Only if these 2 conditions are true. Please let me say this one more time. Both these conditions must be met for a molecule to be polar. Here's an example for you. CH4 has a polar bond, and I knew this because I checked out the delta electronegativity and it told me that it was a polar bond. However, CH4 does not contain any lone pairs, so it is not asymmetrical. It is symmetrical, therefore it is nonpolar. The cyanide ion does not have a delta En that is polar, so its delta En is less than 0.5. It is asymmetrical, however. There are lone pair, but it has not met both those conditions, so it is nonpolar. Here is a guide for you, and it is on the handout that you should have been given. Are there polar bonds present? If the answer is yes, then you have to check and make sure that there are lone pairs on the central atom. If no, it is nonpolar. Only if the bonds are polar and there is a lone pair can it be a polar molecule.